G'day everyone, back to record another little video, this time on continuous random variables, our last chapter, so get excited about that. Just zoom in a little bit. What are we going to be looking at instead of probability mass functions, which were for our discrete data, a probability density function. Effectively the same thing, there's just one little distinction that I will make clear when we're dealing with continuous distributions as opposed to discrete distributions. Measures of center and spread as always. Then we get on to the normal distribution, which will be very important, and you've probably already come across it in a lot of your other subjects. But let's get started and just see what are the differences between what we've learned so far and continuous random variables. Obviously, the biggest difference is for a continuous variable, the variable can take on any value in a particular domain. Because we've talked about this before, whenever we actually have a continuous variable, we still measure to a certain degree of accuracy. There's always some sort of uncertainty in our measurement, even if it's a time and we're using a stopwatch that goes to hundredths of a second. Well, then we're only really doing discrete values that incrementally increase by 1/100th of a second. And so we need to be aware of that. For a continuous probability variable, the actual probability of getting an exact value is always 0. And that's because the exact value exists at a line, doesn't it? A line on the graph. A particular x value is a line. We know the vertical line equation, x equals a number. But what is the width of a line? Well, mathematically, the width of a line is 0. So if I'm trying to find the probability as being the area of that line, the area is going to be 0. So for any particular value, it's 0. So when we're looking at continuous random variables, we're looking at a range of values usually, and that's what we're going to be looking at here. So between C and D, and whether or not we say they're both greater than or equal to C and less than or equal to D, or whether we just use strictly greater than or strictly less than, they're all the same because the probability that it equals either C or D is always 0. So instead of calling them a probability mass function, because a mass, it's got some width, you multiply that by the probability and that's defined as a mass, a probability mass. This is a probability density function. No one else is going to make that distinction for you. Your book does, so I thought I'd better mention it. But let's get on to the important stuff here. When I want to find a probability using a continuous distribution, we're always finding the probability between two particular values. But as always, the sum of all the probabilities underneath our particular function must equal 1. Because we know that the sum of all probabilities for any particular event has to equal 1. And again, it can never have a negative value, can it? Just like all of our probabilities. So we'll do a first little example. You'll find this pretty easy, and then we'll see where we go from there. Consider the PDF, probability density function, f of x equals x squared over 9. And this is defined between x equals 0 and x equals 3. How are we going to go about proving that this is a probability density function? For this one, it just says check that it is. Well, first of all, the visual check, the y value is never negative. So, okay, we know that that's satisfying the first condition. What's our other condition? We need to make sure that the area under the curve is equal to 1. How are we going to do that? We're going to integrate, of course. So we go ahead and you do your integration. The integral from 0 to 3 of x squared over 9, and you can see that that's exactly equal to 1. I don't think that's beyond any of you. Check the working there, I'm sure you'll agree. So if I wanted to find the probability that for this particular distribution, a random result was somewhere between 1 and 2. How am I going to do that? I'm going to do the same thing. I'm going to integrate, except instead of going between 0 and 3, I go between 1 and 2. And you can see there, 7/27ths is the probability of ending up between 1 and 2. Of course, you can use your calculator for this in a calculator exam, but these are easy enough to do with non-calculator in a non-calculator paper as well. So the basic calculation of a probability, it's the same as it always was. We're just finding the area under the curve, just like we did for our discrete variables. It's just this time we have to use integration instead of just adding up the separate rectangles. Measures of center and spread. The mode, not surprisingly, is going to be the highest point on the graph. In that previous example, the modal result would be 3. Interestingly, the probability of any particular result is always 0, of course, so we need to be careful with that, but the mode is just saying that's where it's most likely to occur, around 3 in that particular case. So for a continuous random variable, even though the probability of every individual score in that thing is 0, the probability density function, the probability is more dense, you're more likely to get a result at 3, and that's the point of highest density or greatest density. Median's always halfway through our data, so in this case, in the case above, we'd do the integral from 0 up to a particular point A, which, I don't know, looking at it, I reckon it'd be about there somewhere, but we could, just visually, that looks like about half of the area below the curve. But you actually do the integral. The integral from A, is starting point, in the previous one, that would be from 0 up to some random point M, is equal to 1/2. And then you can go ahead and solve that for M, because we already know what the area is, so we can just go through the working and find out the particular value. That M is the median, of course. The mean, how do we usually find a mean? We take a score, we multiply it by its probability, we do that for every score, and then we add them all together. Well, how do we add up continuous variables? We use integrals, because remember, that's when we looked at where the integral came from. It was adding up infinitely thin little rectangles. That's what we're doing. We're adding up those rectangles. F of x, that's the height of each point. But we need to multiply it by what the actual score was. So score times its probability. We're doing the same calculation. That's just the way we do it for continuous variables. So we'll see that in a minute. Same with the variance. The difference between each score and the mean squared multiplied by its probability. And there's the two different formulae, just like we had for discrete variables. So you can see there, with discrete random variables, we're using the sum, we're adding. With continuous random variables to add, we use integration. But it's the same thing. HL students, the properties of the expected value of x under a linear transformation, if I multiply every value under my normal distribution by 3 and then add 5 to it, the properties that we talked about in the last section still hold. I don't think there are any questions on it in the textbook, but it's important that you understand that those transformations, they work exactly the same way as they did for our discrete variables. Alright, let's look at an example here. Consider the probability density function f of x equals 1/2 x between 0 and 2. Check that it is a valid probability density function. I could go ahead and do my integration of 1/2 x between 0 and 2, or I could just picture it, half x is just a triangle. When x equals 2, it's going to have a height of 1, it's got a base of 2, half base times height, it's going to equal 1. Up to you how you do it. Oh, look, you can see the little picture there. So you could just do the area of a triangle, or we're drilled into, I've got to do the integral, you're going to get the same answer. So either way is fine for that. So yes, there's no value below 0, the area under the curve, between the curve and the x-axis is 1. It satisfies as a probability density function, meets the criteria. Find the mode. So the mode, well, we can tell graphically is the easiest way to tell, isn't it? You just look for the highest value. The mode is clearly going to be 2. That's the highest value of the graph. The median, I want to find where the area under the curve is equal to 1/2. So I'm going to do the integral from 0 up to some particular value m of 1/2 x dx. And then when I do that integral, I'm going to let it equal 1/2. You could just as easily do the integral from m up to 2 of 1/2 x dx and get the same answer. Let's see how they did it, and maybe we'll do it the other way. Just ignore the third bit there. So the median, the integral from 0 to m of 1/2 x dx equals 1/2. I'm going to see if I can change windows, and we can, well, maybe I won't be able to change windows. Let's see if I can type it in. This should be fun. Insert an equation. So what are we going to do? Instead of doing the integral from, get that down a little bit, make our life easier. So instead of doing the integral from 0 to 1/2, I'm going to do from 0 to m equaling 1/2. I want to do the integral from m to 2 of 1/2 x dx. Okay, I'm going to pause and come back with a working so you can see it, because otherwise it's going to take me too long to type it. Hang on, well, it won't seem like much time at all. Right, well that wouldn't have seemed too long for you. Oh, now I've got a nice little blank space in the middle of my, there we go, we got rid of that. Let's see if we can get back and see the whole screen again. There we go. So I've gone ahead and done the working. The integral between m and 2 over half x dx equals a half, because it doesn't matter whether I say the first half or the second half, the area is still 1/2. I go ahead and I work out the calculation, and again I've got to m squared equals 2, so m equals root 2, because m was greater than 0. So finding a median, not a particularly complicated process, ties in some of your calculus with some probability, but fairly straightforward. The mean, what am I doing? I'm doing the integral of each score times its probability, so it's x multiplied by f of x. This is going to be x times 1/2 x, which is how they got the half x squared there. Go ahead and integrate, add 1 to the power, divide by the new power. I've got 1/6 of x cubed, and I'm going between 2 and 0. So it's going to be 8 over 6, which is 4 over 3, minus nothing. So 4/3 is the mean. Finally, the variance. What's my rule for the variance? It's x squared times f of x dx. I'm doing that integral minus the mean squared. We've already got the mean now. It was 4/3, so when I square that, it's going to be 16 over 9. We've got that there. The integral of x squared times f of x, that was x squared times a half x, gave me a half x cubed. Go ahead and do your calculations, and the variance is 2/9. If they want the standard deviation, the positive square root of the variance, root 2 over 3. So the calculations are not too hard. Fairly straightforward usually, not trying to make it too complicated for you, and it's a good chance for you to just show your understanding of integration and how the areas under the curve are representing probabilities. That's the main thing. Moving on to what you have probably heard of, the normal distribution. Normally distributed variables come up a lot in nature. The heights of students in your year level are presumably very close to a normal distribution. Most things that are measured in nature tend to follow a normal distribution. There are exceptions, but in a lot of cases, this is exactly the type of distribution that they follow. It may be that it's a distribution with a small standard deviation. If it's got a smaller standard deviation, I'm just going to draw with my pen here, so this should be fun. It might be steeper and more bunched together. It's got a smaller standard deviation. If it's got a large standard deviation, it's spread out over a greater range of x values, or a larger domain if you like, but the area under the curve is always equal to 1. When I've got the probabilities vertically and the possibilities along the bottom, the area under the curve is still going to equal 1. Okay, look at how we can compare these different normally distributed data in a second. But for this, there are certain properties that are always the same. The mean is always the center of the distribution, it's always right in the middle. And it's also the median and the mode. So for a normally distributed data, the mean, median, and mode all occur at exactly the same value. To write this, just like we wrote x tilde b for binomial distribution, we always define that by n, the number of trials, and p, the probability. A normal distribution is defined by the mean and its variance. Why they choose variance and not standard deviation is a good question, but that's how they do it. So mu and sigma, little mu and little sigma, respectively, the mean and the standard deviation of the population, they're the parameters of the distribution. Parameters, remember, population statistics, not population parameters, not sample statistics. The probability density function of x is actually given by this equation here, which of course came from Gauss, who did pretty much everything in maths. If Euler didn't do it, it was Gauss who did it. We don't need to memorize and know that formula, but just be aware that it's just it's a formula for which we can find an integral, and it works the same way as every other equation we've dealt with. It just produces this sort of curve. Again, they're just talking about it's symmetrical. It's an asymptote here, so you can never go below the x-axis. Well, we knew that because we can't have negative probabilities, and the maximum occurs at the mean. All very good. Something we may not have heard before, a point of inflection, remember a change in the curvature of the line, always occurs one standard deviation above or below that mean value. So mu plus sigma, that's the mean plus one standard deviation. Mu minus sigma, the mean minus one standard deviation. So when you're drawing it, you can always, if you're just doing a little sketch, try to keep that in mind, that within one standard deviation, that's where you change your curvature. Interestingly, because normal distributions all have similar properties, a very interesting fact is true. Within one standard deviation of the mean, so plus or minus 1 sigma, which is where that point of inflection is, approximately 68% of all values lie. So if we're talking IQs where you've got a mean of 100 and a standard deviation of 15, then, or at least it was, I think it's actually changed a little bit now, but then 68% of people would have had an IQ between 85, 1 standard deviation below the mean, and 115, 1 standard deviation above the mean, where the mean was 100 and the standard deviation was 15. 95% of people are within 2 standard deviations of the mean. And within 3 standard deviations of the mean, you've got 99.7 approximately % of people. These are good for a rule of thumb. If you don't need a lot of accuracy and you're just trying to see roughly where values lie, that's all you need to do. Within 1 standard deviation, we've got 68%, 2 standard deviations, 95, 3 standard deviations, 99.7. What does this look like? In an example, a sample of cans of peaches was taken from a warehouse and the contents of each can was weighed. The sample mean was 486 with a standard deviation of 6. State the proportion of cans that weigh between 480 and 486. So, we've got a situation here. Again, I'm drawing with my mouse, so we'll see how we go. 480 is the mean. That looks like 480 almost. The standard, so we always write this underneath. Mean equals 480. Standard deviation equals 6. So when I'm looking between 480 and 486, isn't that just painful for you guys to watch? It's asking me, what's this area in here? And you can see, I know we called it the 68, 95, 99.7 rule. 68, it's 68.26. So 0.3413 or 34.13% of scores lie within that range. Here again, they're just saying, oh, I did 480 to 486. Was it 486 was the mean, and they wanted between 480 and 486. So actually, shift that one to there, that one to there, and they were finding that area. Serves me right for trying to draw with a mouse, distracting me from reading correctly. But again, it's still within 1 standard deviation of the mean, so it's still the 34.13%, or 0.3413 is the probability. More than 492, if this was 486, another standard deviation would get us to 492. So we've got 50% below the mean, another 34.13%, so now we're up to 84.13. So the remainder, the 15.87, 0.1587, lies to the right of that value. And you can see that's how you do it there. You've marked in your 492. We're looking for the area to the right. You could add those little values from this diagram, or you could do the total. It was a half up to that point, another 34, and go 1 minus that. You're not always going to be given such beautiful, nice values though, are you? So I better check how would we actually do these calculations on our calculator. So again, we're going to go to statistics mode. We are looking at, just press number 2, does it? There we go. We're looking at a distribution. It's a normal distribution. Normal cumulative distribution is the one we're after. We will list it as a variable, that's fine. The lower value in this particular case, the first one here, I wanted to know between 480 and 486, so I just type in 480. My upper value, 486. The standard deviation was 6, and the mean value was 486. I'll get it right this time. And so you just go ahead and do your calculation, and it tells you 0.34134474. So it goes to a little bit more accuracy, unnecessary in our case, but we know, and the Z, interestingly enough, it's telling you the Z-score of each of those values that you put in. You haven't met a Z-score yet, but we're going to in a second. And a Z-score is just, it's a standardized normal score. It's just telling you how many standard deviations from the mean each score was. Well, we knew it was 1 standard deviation below, and the upper limit was our mean value. So it was 0 standard deviations from the mean. That's what the Z low and the Z upper mean there. But the value 0.3413, we can see that's exactly the same as when we used the 68, 95, 99.7 rule. Just going to change that back to that because it's annoying me. Alright, what about when I'm doing the next one? I wanted to know greater than 492. So I have 492. Now you have to choose an upper limit. But this is a continuous function. It goes on forever in theory. So how big a number do I choose? You can just mash your 9 button. You can go 9 exponential 99, something like that if you like. It doesn't really matter so long as you are at least 5 standard deviations above the mean. So it would have been just as easy for me to go, oh, well, 5 times 6 is 30. If I add 30 to that, 516, that will give me roughly the same value. Let's have a look. I'll do 9 times 10 to the 99 first, just because I'm difficult. 0.15865525. That's a 0.1587 roughly, 0.15865. Round to that, that's fair enough. If I, instead of using that massive number, I just had used 516, 0.15865,496. So there's a slight variation at the end of the number, but we're already to the 5th decimal point, more than accurate enough. So if you're going at least 5 standard deviations away, you will be fine when you're doing those calculations. So that's how we're going to use our calculator to do those questions. Nearly there, you guys are doing well. We're 20 minutes in, but not long to go now. And then it's another chapter down. How exciting is that? So I mentioned it just a second ago. The standard normal distribution, a Z-score, to work out how many standard deviations above or below average a particular score is, you take the score, you subtract the mean value, the average, so now you're finding the difference between the score and the average, and then you divide it by sigma, divide it by the standard deviation. So now I'm knowing what this score as a fraction of the standard deviation is telling me how many standard deviations above or below the mean I am. If I'm above the mean, x minus mu will be positive, so I'll have a positive z-score. If I'm below the mean, x minus mu would be negative, and I'd have a negative z-score. The interesting thing is that eventually, when you do this distribution, the z-scores are still normally distributed. The mean value is going to be 0, because the mean value of a normal distribution is mu. When I go mu minus mu in that first bit of the calculation, I'm going to get 0. So the mean value is 0, and the standard deviation is 1, because it's clearly going to be working out 1 standard deviation away. When I go 1 standard deviation divided by sigma, I'm going to get 1. This is useful because all these different distributions that we talked about when I drew these weird shapes up here, when you standardize them, when you convert them to z-scores using the standard normal distribution, they all follow exactly the same pattern, which means we can now compare results in differently normally distributed data sets to see which one is more unusual or which one stands out. And we'll give you an example of that in a minute. Here we go. Kelly scored 73% in history, and the class mean was 68% with a standard deviation of 10.2. In maths, she scored 66%, so not as good as she scored in history in terms of raw score, but the class mean was only 62 and the standard deviation was 6.8. In which subject did Kelly perform better? So that's a really interesting question. When you're doing these questions, I encourage you to initially make sure you draw a normal distribution. I'm going to pause again and change windows so I can actually write on the screen this time, and we'll go through the rest of it. Alright, I'm hoping this is going to work. We'll see how we go. So Kelly scored 73% in history. So what we want to do is we want to find the z-score for each of these performances. It'll help if I have a pen, not the eraser. So Kelly's z-score for history. And remember, define your variables. Kelly's z-score for history. And let Zm be Kelly's z-score for maths. So I'm going to have her z-score for history is going to equal her score, 73, minus the mean, 68, divided by the standard deviation, which was 10.2. Her z-score for maths is going to be her score, 66, minus the mean, 62, divided by the standard deviation, 6.8. We go ahead and figure that out. Here I've got 5 over 10.2. Why don't I make that 50 over 102? And then we can simplify that to 25 over 51. So it's pretty much half a standard deviation above the mean. A Z-score just over 1/2, 25, or just below 1/2. How silly of me, 25 out of 51. The Z-score for maths, 66 minus 62 is 4. It's going to be over 6.8, so I'm just going to rewrite that as 40 over 68 to make my life a little bit easier. Oh, well, 4 goes into all of those, so I'm going to have 10 over 17. Z-score for history, less than 1/2. Z-score for maths, more than 1/2. So which subject did she perform better in? It's actually maths in which she had the better performance. And I've pre-copied the answer in here so we can confirm that we got exactly the same calculations. Here they've converted them into decimals, which is fine. It would probably be in a calculator exam, so that would be all right. So Kelly's result in mathematics was a better performance relative to her peers than her score in history, even though her history mark was higher. Not that it affects you guys as much, but in the QCAA, this has a big part to play in determining their ATAR. It's important that your performance relative to the performance of others in the group is important. Last little thing we want to do is look at normal quantiles, so just percentiles, really. Why might we do this? It may be that you want to award a scholarship or a place in a particular program to the top 5% of people who apply to a particular course. Well, if you know the mean and standard deviation of all the scores of the applicants, then you can easily find where the 95th percentile is. What's the cutoff required? So here's an example. In this case, we're looking at a population of crabs with a shell length X millimeters. And we know that these crabs have shell lengths that are normally distributed with a mean of 70 and a standard deviation of 10. Find the K value for which the probability X is less than that is 0.95. It's always good, and I would say mandatory, to draw a little sketch of these before you start. Here I know that the mean is equal to 70 and a standard deviation is equal to 10, and they want to know what's the particular value K so that this area, the probability that X is less than K, is equal to 0.95. So the way we do this is we do the normal distribution function in reverse. We actually use the inverse normal function on our calculator. So let's go ahead and look at how we do that right now. So we're going to statistics again. Whoa, it's zoomed in really close now, isn't it? Can I change the view to small? It's already small. Oh well, we'll see how we go. I'm going to go to statistics, number 2. Let's exit out of that. I want to go to distributions again. I definitely want a normal distribution. This time I'm going to use inverse normal. It's a variable. The tail is to the left. I could have the tail wherever I like. In this particular case, the tail is to the left. The area of that tail, is it going to let me get to the 0 so I can type in 0.95? Oh, maybe I can just do it on my keyboard. That's a better way. The area is 0.95. The standard deviation for this one, let's go back and check our values. Standard deviation of 10 and a mean of 70. So I enter my standard deviation of 10, my mean of 70, and we go ahead and calculate the value of K. And that value of K is 86.448. So 3 significant figures, let's call it 86.4. So how are we going to set that out? Well, that's fine. The probability of K, of X being less than K, equals 0.95. Therefore, K equals approximately equal to 86.4 is all you need to do. The instructions, if you had a different calculator or you want to just check it again, right there, if we zoom in a little bit more, they'll almost be legible. There you go. Now, I did say we could do it the other way. I could have had the tail to the right, so let's just confirm that that would be the case. If I do the tail to the right, press F2 there, the area of that tail to the right is 0.05. And again, I'm getting the same value. So you can see it doesn't matter which way you like to think about it. As long as you've drawn yourself a nice little distribution there, you're going to have not too many issues with that. Almost done. Finding an unknown mean or standard deviation. in certain situations, we may know some information and we need to work back to find the unknown mean or the unknown standard deviation. Let's look at one of those now. The weights of an adult scallop population are known to be normally distributed with a standard deviation of 5.9. 15% of the scallops weigh less than 58.2. Find the mean weight of the population. So I've got my normally distributed population. The mean, I don't actually know. But I do know the standard deviation of 5.9 grams. 15% of the scallops, so an area of 0.15, weigh less than 58.2, so that's my value in there. How am I going to go about finding this mean? Well, we have to go back to our Z-scores. Remember, a Z-score is the value of a particular score minus the mean divided by the standard deviation. So if I do inverse normal for a standard normal distribution, remember a standard normal distribution, Z-scores have a mean of 0 and a standard deviation of 1. If I do the inverse normal of 0.15 for a standard normal distribution, effectively what I'm doing is saying I'm converting this original distribution into the standard distribution with a mean of 0, a standard deviation of 1, and I want to know what Z value is going to correspond to that 58.2. So when this area is 0.15, what's the Z value there? That's what I'm looking for. And so we're going to do inverse normal on our calculator again. Tail to the left, area 0.15. Tail to the left, area 0.15. So this is saying that 15% of the scores lie below a particular value. I'm not doing my previous example. In this case, the standard deviation is 1 and the mean is 0. I can always use my standard normal distribution to find a Z-score. So I've got negative 1.0364. That'll be enough for our purposes, I think. Negative 1.0364. What can I do with this now? Well, I can substitute it into my Z-score rule. So Z was negative 1.0364. What was the X value that gave me that Z-score? It was 58.2. The mean, I don't know. That's what we're going to go ahead and try and find. And the standard deviation here was 5.9. So now it's just a bit of rearranging. I can multiply by 5.9. Multiply that by 5.9, and that would equal 58.2 minus mu. So if I add mu to each side and add 1.034364 times 5.9, I'm going to get the value of mu. And we can go ahead and do that on our calculators. Menu. So we can see what it is we're trying to calculate. Okay, I'll do it the other way. It must be annoying. Ha! 58.2 plus 1.036455.9. And it's saying the mean is approximately 64.3 grams, I think it was. You go up and you check. In the question it says that, and of course you write a nice little statement. The mean weight of the population of scallops is approximately 64.3 grams. Hopefully we got that correct. I thought I included a little image of to expand to see the results. So that's okay. We'll go over here and see it in the actual book. You'll be able to find it as well. Where did I have that example question? Oh, there we go, 64.3 grams. So you can see how easy those calculations are. Normal distribution, it's actually kind of interesting. It's great. It helps settle some arguments sometimes when you're talking about when one particular sportsman was better than another one or something. You can look at their statistics, how many standard deviations above or below the mean they are, and then you get an idea about who was actually the most superior performer. Also, just when you're looking at your performance in different subjects, some subjects are more difficult than others based on the results that students get, so you get an idea about which is a superior performance, which was more impressive. Anyway, that's it for our continuous random variables. A little bit of a marathon there. Hopefully that made some sense. At least we've got that to go back and look at, and we'll talk about it in class soon. Thanks very much for your time. Good luck, guys.